But before we introduce you, this is broadcast on Zoom, so I will remind everyone on Zoom, please unmute yourself, and it's recorded. So if you say anything embarrassing, this will be forever on video on YouTube. So don't say anything stupid. Other than that, until about 5 minutes ago, we could hear when people were speaking on Zoom, and now it doesn't work anymore. I have no idea why, and now it's too late to fix it. So if you do have any questions, I'll try to get it working at the end, and if it doesn't, you can just write in the chat, and me or someone else will read them out loud. I would recommend to avoid asking questions on the chat during the talk, because it has those annoying pop-ups, unless it's something urgent. That's fine, but otherwise do keep that to the end. Okay, I'll invite Greg to introduce our speaker for today.
Thanks, Michael. Well done with the tech, that looked confusing. Okay, so it's my great pleasure to introduce Jörg Hermann to you. Now, many of you will be very familiar with Jörg, both personally and through his scientific achievements. Jörg did his undergraduate and a master's and a PhD at the famous ETH in Zurich in Switzerland. And then in 1998, him and Daniela landed here as postdocs to work with David Green, who was the then director of the school, in the experimental petrology area. And that worked out fabulously well. And in fact, in 2005, Jörg became a member of the faculty here. He stayed until 2015, where unfortunately him and Daniela decided to move back to Switzerland, where they are now at the Institute for Geoscience in Bern. So Jörg would describe himself, I guess, as a metamorphic petrologist and an experimental petrologist, an alpine geologist as well, geochronologist. He's many more. He's very diverse, and his work has been covering a huge range of broadly geochemical and petrological fields, extending out into other areas as well. He's amassed a tremendous list of publications and other achievements. He was the winner of the Dana Medal in 2018. That's for the Mineralogical Society of America. And just a couple of weeks ago, he was well, it was announced that he was going to become a fellow of the Geochemical Society, which is kind of a peak achievement in the field of geochemistry. So it's really good to have Jörg and Daniela back here for a few weeks. And he's going to tell us about the Earth's deep volatile cycle. So thank you.
Thanks a lot, Greg. It's a great pleasure to be here. Great honor to talk here in this room. And what I want to do today is to provide a link between the deep volatile cycle and continental crust formation, a few aspects in this very big and vast topic. This has been work in collaboration with Daniela, Thomas Petke, Pia Lanari, colleagues in Bern, Carlos Canadi that visited for a year, postdocs, Pete Tolan, Noelle Tamblin, and then students, Shane Lakey, that did experiments just down the hall. I will show some of his results and the elaboration we did afterwards, Elias Kemp, Julian Rein, and Matthias Lehrer. So when we landed here and took the apartment nearby Belconnen, opened the cupboard and saw these guys here, salt and pepper made out of serpentinites, and the kitchen bench is out of granite. And actually these two things symbolize the essence of the talk I want to give today. And that is how the dehydration of these type of rocks, the serpentinites that we see on one hand, trigger ultimately crust formation that then produce the granite. So in a nutshell, it was all there waiting for me. And that was actually the starting point to put this talk in this form together. So let's start with the deep water cycle. Just where do we see deep water cycles? We can have deep water cycle within the crust, where we have weathering, burial of the rocks, dehydration, and then fluids coming back up, operating at timescales of 0.1 to 10 million years. Arguably, the biggest deep water cycle is subduction water cycle, where we have uptake of water in hydrous phases close to ocean floor, transporting down and having then a series of dehydration reactions, returning water back to the surface at timescales of 1 to 10 million years again. But then we have also a third one, third water cycle that operates at much longer time scales, and that is that we can have water trapped here, either in hydrospaces or in nominally anhydrous minerals that subduct to the transition zone, to the deep mantle, to the core mantle boundary, and eventually turn back to the Earth's surface at the mid-ocean ridge spreading. And these very deep and very large long-term water cycle may be operating at hundreds to thousands of millions of years. Now we're going to just a very rough first constraint on this cycle. It is instructive to look at the outputs. So on mid-ocean ridge, we have, you produce yearly about 20 cubic kilometers per year of new material. Water contents of these basalts is 0.1 weight%. If you compare that to the arcs, where we have only about 5 cubic kilometer per year new material added, so that is 4 times less, but the water contents of these primitive lavas might be around 4 weight%, so 40 times more. So we see that through this simple mass balance, we would say that about 10 times more water is recycled through the subduction, recycling system than through the deep water recycling. But if we do this assumption, we kind of imply that our system is in a secular equilibrium, so that inputs and outputs are leveling out. And this is actually one of the questions that we are not sure of. And especially what is important for the division of these two cycles is, of course, this critical region here in subduction, recycling, formation of new crust. And that is the main focus of the talk today. Why are we interested in all these things? And that is water is one of the defining elements of the behavior of our planet. Now, it affects so many different things. We will have a look at the melting behavior, maybe a little bit on the density, but it affects also other properties, like can have effect on seismic wave speed, on rheology, on diffusion properties, on how the magmas differentiate, how metamorphism takes place, how eruption dynamics is, you name it. Water is really a key ingredient for the processes on planet Earth. And this, in a nutshell, is kind of the link that I will now then elaborate is that we have, that's the current paradigm, that we have dehydration of minerals that are subducted. In subduction zone, the increased temperature and pressure leading to breakdown. These fluids then will interact with other rock types on top of the slab. Here, for example, using melting of sediments. And then we have these, that through the water added, we have a depression of the solidus in the mantle, and we produce wet melts here that then will differentiate in a particular way and create explosive volcanism. And at the end of this refining process, we have the granites that form the typical igneous rock type of continental crust. And as such, I just made this very bold statement when I talked to colleagues from a Space and Habitability Center in Bern. Now they're looking at exoplanets. They are interested in, is there water cycle? Is there the life? Is a thing? I say that granites would be one of the good markers to say that a planet might have a deep water cycle. So that is in short the process, but now we want to dwell into the detailed processes that make this link between the dehydration and then ultimately the crust formation in the subduction zone setting. And the approach that I want to bring you a little bit closer is, as Greg said, liking to combine different fields of petrology. So we will have some field work, some petrography, petrology, and experimental as well as advanced analytical techniques, and jump a little bit forwards and backwards between these different things. And I have structured the talk into 3 main blocks. The first one is that we look at the production of the fluid, that dehydration reaction, and on how that might impact some properties of the slab-mantle system. Then once we have established the dehydration reaction, we will see what these fluids do with the overlaying all the crust, or especially the sediment. So we look at fluid mediated mass transfer out of the subduction system and have a look at a few case studies. And then finally, we'll dwell into the deep water cycle, because at the end of the second block, we see that there are some complexities that need to be considered that will have impact also on the deep water cycle. And then I'll finish with an outline. Okay, so the first block, dehydration in subduction zone. And that sounds, now when we teach that to our students, it's always very simple. Yeah, we hydrate, then we bring it to higher pressure and temperature, dehydrate, and the fluids come out. But when we look at that problem of dehydration, it is actually quite a complex problem between different fields. So let's start here on the left-hand side with a picture here from Peacock, from Simon Peacock. What we want to show is the first order observation is that we have this cold finger of the subducted plate going into the hotter mantle. And that produces a strong thermal gradient. And what we are interested in when we look at the dehydration reaction is we need to know the temperature that is on top of the slab where our rocks are hydrated. And this temperature might depend on many different things. For example, the age of the plate speed. It might also depend on the boundary. Is there friction? Is there coupling? Is there decoupling? It also depends on the mantle wedge temperature and if the mantle is stagnant or is flowing. And this leads to quite different scenario that we can put up, and different models have different solutions to that. And these models, they might differ by not just a few degrees. These are hundreds of degrees that we are talking between different sets of models. And this, of course, will then impact on the position of the dehydration reaction, because that is then the second part of the problem, is the petrology side. So what we normally do on the petrology side, we show these key dehydration reactions in a pressure temperature space. So temperature would be again here the top slab temperature, and the pressure would be corresponding to the depths of the rocks in the subduction zones. And so we can take then, for example, here would be one set of solutions of such slab geotherms, and then we combine that with the position of these dehydration reactions. Here I've shown the three key dehydration reactions in ultramafic rocks that we will follow through the talk. And we see that then we can gather from this that we have at different depths on temperatures, we have this dehydration reaction. But in order to know where this occurs, we need actually good constraints on these dehydration reactions, where they occur. And again, if you use different methods, if you look at calculated phase diagrams, if you look at experiments, if you compare simple system or complex systems, the position shift with then the implication of this being that the depths of where we release our fluid now is, it might be that we then release all our fluids before we reach a depth of where the volcanic front is, or if they go far too deep, because at the end we want to have these dehydration reactions in a place so that then the volcanic front can be formed through fluid flux melting of the mantle wedge. Okay, so now let's go to the real rocks, excursion to my favorite field area to Zermatt. And here on the right-hand side, you see spectacular rock types. So these are pillow lavas that you see still nicely the shape of the pillows. But if you zoom in, you see that these are now fully metamorphosed in a rock that is consisting of garnet and of amphasite, that is an eclogite. So showing that these ocean floor rocks have been subducted to eclogite phase conditions, about 25 kilobars, 550 degrees, corresponding to the depth of about 80 kilometers in our subduction zone. In this particular case, this is related to the subduction of the Piedmont-Ligurian Ocean that has separated Africa and Europe, and now this oceanic slice is sandwiched in between. What we also see, though, is when we look at these rocks, garnet and amphasite rutile quartz in here are all nominally anhydrous minerals. So our hydrated oceanic crust has lost already all the water when we reach these 80 kilometers depth. And they are essentially dry eclogites. So if we want to bring water to the subarctic depths, we need other rock types. Their hydrospaces are stable to greater depths. And we don't need to look far in this picture here. Below the Matterhorn, we have these beautiful other associated rock types to these eclogites, which are serpentinites. Serpentinites normally have been considered in the past as a typical green schist facies metamorphic rock. But here, in cases like in Zermatt, we can actually show that serpentinite is an eclogite facies rock and forms here at about 550 degrees, about 2.4 gigapascal, so these 80 kilometers depth. And when we look at these rocks, they are highly sheared, and we have this first partial dehydration of antigorite and crustite going to olivine, chloride, and water. So a first water-producing reaction. What we also see is that in this reaction, the production of fluid is limited by brucite, which might be there or might not be there. And antigorite, the main serpentine mineral, is still stable, as we can see here nicely in these rocks, or here in this zinc section. All the transparent sheet silicate here, that is antigorite. So meaning that at 80 kilometers depth, we can have still large volumes of these serpentinites made out of sheet silicates that are very weak and that show a strongly preferred orientation. And that is for seismics, that is an interesting aspect. Now that is, if you have a thick enough layer of rocks with large seismic anisotropy in the minerals, could mean that this is a signal that could be picked up by seismics. Another thing is also that it is quite important for the rheology of the rocks, because these are lubricants. These are very weak rocks at the slab-mantle interface. And this means that in the part where we have serpentinite still stable, that is here in this sketch of Wada and Wang, the stagnant mantle wedge where we have the partial serpentinization, here we have a decoupling of the movement from the down-going subduction slab and the mantle wedge, meaning that this mantle wedge will not move. And it's only when we break down the serpentine that we start to have a coupling between the down-going plate and the mantle wedge. Now, if we start to have a coupling between mantle wedge and the down-going slab, this in turn has implications then on the heat flow structure that can be observed on top of the arc. So, Wada and Wang, they showed that if we wouldn't have any motion in the mantle wedge, that would be the heat flow observation here. Instead, what is observed that then it goes back up. And this can only be maintained if there is this coupling and the mantle wedge is turning with the subducting plate. Now, this in turn then has influence on the thermal structure, the temperature that we have on top of the slab. Because if we have here the always new hot material that comes in, we can heat up the mantle, the top slab significantly over a relatively short distance. And that is shown here in these geotherms. That is why these geotherms have this sigmoidal pattern, that over a small pressure increase here, we have a strong temperature increase. And that in turn has implications of where we dehydrate. So the coupling of the rheological properties of rocks with the thermal state of the subduction zones and the dehydration reactions. But what we also see is now it's quite important that we pinpoint where these last occurrence of serpentine is, because that will determine where we have the decoupling to coupling occurring. So very important to see that this antigorite breakdown occurs, and that can be observed here. An example from Sierra de Almenes in Spain, the best location where this can be studied, where we have here on the right-hand side still our highly foliated serpentinites, as we can see, weak rocks easily to deform. And then on the left-hand side, we have the dehydrated equivalents. Antigorite has been consumed, and we have the secondary Harzburgite here, a granular Harzburgite, and here is spinifex type Harzburgite. Much tougher rocks, much more difficult to deform. So we want to know where exactly in PT space this transition takes place. And so that is Jose Alberto Padron Navarrete has done experiments also down the hall here a while ago. Here we see at 16 kilobars, 640 degrees, our antigorite is still stable, coexisting with some other phases. And then when we heat up to 680 degrees, 16 kilobars, we see that we have the secondary half-spherites consisting of olivine, autopyroxene, and chloride mainly, with minor tremolite in this case. And so what Alberto did is then he compiled a set of these experiments, determined the antigorite out reaction, and from the position of this reaction compared to the calculated simple system serpentine breakdown, he formulated a thermodynamic model of aluminium incorporation into antigorite, so that then in later studies, in next studies, we were able to calculate where the dehydration reactions in these systems, in more natural-like systems are. And here's just an example of such a phase diagram where we see our three main dehydration reactions. So that's the antigorite brucite, and here is the antigorite breakdown reaction, and that would be the chloride out reaction. And we can then see how much water is liberated over what temperature interval along this reaction. And what we see is that there are kind of three discrete pulses. It's not all smeared out over large temperatures. So there's three relatively narrow temperature ranges where we liberate at once 2.2 weight%, here 5%, and depending on composition, that can be up to 12%. And here would be another 2.7 to 3 weight% of water that are liberated here. And the question then is, what happens if we have these kind of near pulses of fluid liberation? What does that do to the slab? And one argument that has been proposed is that these might be the triggers for hydrofracturing, so that subduction earthquakes could nucleate from places where we have these fluid liberations, large fluid liberations over very small temperature intervals. Another thing, maybe just for the structural community that is of interest, is that in the fields here where we have no nominal dehydration reaction, we still produce tiny amounts of fluid as the rocks go on. And that means that we always have, or we likely have, wet grain boundaries as our rocks deform. And that is important for the recrystallization behavior of these rocks. So they are never really truly dry, but three pulses of fluid liberation. So now we have established 680 degrees is the point where we have our termination of the coupling, is the where the antigorite disappears. But now when we look at arc settings and look where the position of this decoupling is with respect to where the main volcanic arc is, we always notice that it's not really that the dehydration of what comes here then would need to move down here, complicated, and get here into formation of lavas. Very complicated, very difficult. Fluids tend to kind of like to move upwards or along the slab-mantle interface. So the question then is, where are the fluids produced that trigger the wet melting in the slab? And so what we need to focus now is on the third dehydration reaction, that is the chloride dehydration reaction. So the two main scenarios on how we can produce or get fluids into this subarc region is, the first one is that we focus on these chloride-rich rock types. And what field studies have shown is that at this plate interface, we can have a mixing between mantle material and crust material, and the result of that is that we can have chloride-rich metasomatic rocks. And now what we need to test is at what positions do these metasomatic chloride-rich rock types dehydrate, and if that could be a source for fluid for melting than other slab materials. The other solution is that we say, okay, antigorite breakdown is not occurring at the slab-mantle interface, but is occurring in our oceanic lithosphere. Now that what goes down has 7 kilometers of oceanic crust below is mantle, and if we hydrate that mantle, that is at colder temperatures as our slab goes down, and therefore the dehydration of a partially serpentinized lithospheric mantle could also produce fluids that then interact with sediments as they move. But now we want to focus quickly on the scenario to look at the chloride-rich rocks. Now here, a whole lot of experiments from Shane. I don't want to go into too much detail. It's just to say that what you observed is that the chloride breakdown occurs over a temperature interval of about 100 degrees. And when we look in detail, in order to see what type of reactions that we have, we can constrain three main fluid producing reactions. So here we start at 700 degrees. We see nice the shapes here, the lots of chloride, and no garnet yet. We go to 750 degrees, clinopyroxene disappears, and we form new garnet, and the reaction would be the clinopyroxene and the chloride goes to olivine, garnet, and water. Then we have a second reaction where the chloride reacts with orthopyroxene, again forming olivine, garnet, and water. And if we have very chloride-rich rock types, that means that we exhaust clinopyroxene in the first reaction, we exhaust orthopyroxene in the second reaction, we can reach the terminal breakdown reaction of chloride going to olivine, garnet, spinel, and water. And then from these many experiments, we do phase petrology analysis, Schreiner markers, and so on, and we come up with we can construct a phase diagram. And here it is. So these would be these three, the sequence of these three chloride dehydration reactions. And one thing to mention is that we see here the antigorite reaction that we discussed before. In earlier studies, the chloride dehydration reaction crossed over here at about 4 to 5 GPa with the antigorite reaction. We don't observe that. So the antigorite breakdown and the chloride breakdown are always nicely separated. Okay, so now we have more or less established the framework on how we liberate the water. What we now want to know is how that goes into influencing mass transfer. So we go into the second part of the talk on and talk about the fluid-mediated mass transfer. So just very schematically, what we want to know, we have our brucite, antigorite, chloride dehydration. And of course, we know with a fluid that comes out of a serpentinite will never produce a granite because on top of the subduction system. Because we know very well, Richard pioneered, we know that we need to enrich, we need to transport large iron lithophile elements, all the rubidium, the strontium, the potassium. It's very important also for all the heat producing elements. Now the potassium, thorium, uranium. Recycling, very important for the overall heat budget of this. How much is in the crust, how much in the mantle. So in order to understand the recycling of these key elements, the sediments and the altered oceanic crust are key components. So what I want to show you now is how these fluids that are liberated from the ultramafic rocks interact with the main trace element host, that is the sediments, in order to get the subduction component then leaving the slab. So what we need to do is have a look at the fluid sediment phase diagram in a very simple form. And what we see, we have two regions here that are separated by the wedge solidus that then disappears on along a second critical endpoint. And without going into the detail, is here on the left-hand side, when we look at experiments, here we have very water-rich fluids and very little solutes in here. As we move here into this intermediate field, we see a mixture, we have more dissolved stuff that then precipitates here as these spheres. Then here we are already in a field of a hydrous melt with a lot of volatiles that then forms this bubble. And then here we have proper hydrous melts as we move to the higher temperature region of the diagram. So what we see is that we have these two main regions that we have, and if you have our slab geotherm, we can now assess how much material can we remove from our slab as a function of how much water normalized to the amount of water that we have, because the water will be the limiting factor on how much stuff, how much material we can move. And if we do that, so I show you now experimental results when we analyze these fluids with on trace elements, we can then have this type of curves. So this is element removal in weight percent. So for example, how much SiO2 in weight percent we extract from the slab per weight percent fluid that we flush through. And what we see is really that we have these two regimes. So that's a logarithmic scale. These huge variations. As long as we have an aqueous fluid, we will need to put a lot of fluid through to remove very little material. But as soon as we go into the hydrous melt region, we have a very efficient way of stripping these key elements out of the slab. So here is silicium, potassium, cerium, and barium. And just on the potassium water, maybe a little side information. This is actually quite a nice ratio of potassium and water, because both are very incompatible in the mantle wedge, and in the normal mantle wedge are very depleted. So the potassium and the water that we see coming out in our lavas, at least 95% of them must derive from the slab. And this in turn can help us then, if you look at the range of potassium water contents in our lavas, help us to constrain or give us an idea at what temperature these fluids have been extracted, assuming that the potassium H2O ratio has not been modified very much through the, on the transport. That's a different topic we could discuss another time. But if we do that, then it would imply that the temperature range below the arcs would be in this kind of 750 to 900 degrees. Okay, but take-home message here is if we want to efficiently remove material from the slab, recycle and form new crust, what we need are hydrous melts, the aqueous fluids going to the tube. Now we overlay on that the position of our dehydration reactions. So we build that up, and we have the brucite dehydration reaction, and the left sharp boundary would be the dehydration on top of the slab, and towards the right would be meaning if we have dehydration moving into the slab to deeper levels. And so what we see here is that again, with brucite, we produce very dilute fluid. Antigorite on top of the slab is still in the field where we have aqueous fluids, and only if you have antigorite dehydration in the deeper parts, we would then have melting on top of the slab and significant removal, no problem when we have chloride. So chloride dehydration might trigger this efficient slab transfer of material from the slab to the mantle wedge and then to the new crust. So if we now overlay this, I showed this one just a few minutes ago, with the information that we gathered now. So here would be our wedge solidus. Here would be typical subduction geotherms. Here's Tonga, Kamchatka, and the hot one for Cascadia. We could then predict kind of where would be the dehydration reactions and in what position with respect to the wedge solidus the interaction would take place. And overlaying on this graph with red is the compilation of Cooper et al. That tried to constrain the slab conditions below volcanic arcs. And what we see is that there is this nice straddling of these constraints with our chloride dehydration reactions. So from this, it is a suggestion that indeed chloride dehydration on top of the slab might be an important process to melt associated sediments, and that is an important means of mass transfer into the mantle wedge and then formation of new crust. Okay, so I've been talking a lot about natural examples. I want to quickly just browse through and say that that is important also then when we have this hypothesis to look at natural rocks. See, can we see that? And I won't go into detail, I'll just give you the main important information. So we go into the Central Alps, close into Ticino, Italian-speaking part. We have beautiful metamorphic ultramafic rocks. They have dikes of mafic rocks associated, showing that this is a suite of mafic, ultramafic rocks, and that the ultramafic rocks here, they have pseudomorphs after garnet, indicating that these rocks went through the chloride dehydration reaction in order to form garnet-peridotites. When we look at the associated aquagites, we see classical aquagites with garnet, clinoparxene, rutile, and kyanite, and we do the thermometry of these rocks. They return temperatures of about 800 degrees, pressures of about 2.8 gigapascal. And if you plot that on our previous phase diagram, we see nicely straddling this autoparxene plus chloride dehydration reaction. So we have a system here of mafic, ultramafic rocks, one dehydrating exactly at the conditions that are recorded by the aquagites. So the question is, do we see evidence of this partial melting, this interaction of chloride fluids with the rocks? And indeed, when we have a zoom in, we see that we have a migmatization here of our aquagite. We have these leucosomes here, and these leucosomes are still stable together with garnet, meaning that is still a melting that formed at high pressures. If you look in detail, we can map out melt pots or melt distributions with the potassium, for example, in these melt pots, or here we can also do just with our electron microscope, see beautiful here interstitial pockets of melt that crystallize to plagioclase quartz, and here we have new zircons. If you look at these leucosomes, they are chondromitic, high in sodium, relatively low in potassium. They are depleted in the heavier earths, enriched in the lighter earths, and they have positive anomalies of lead and strontium. So as we would expect from a typical subduction zone melt. And now just one small little top is that we have, when we look at the zircons, now we have seen that we have these beautiful zircons here in these leucosomes forming. And again, without going into detail, the protoliths, they are Permian or they are Jurassic in age, and they have oxygen isotopes that are here for the Jurassic at 6 per mil, and the Permian ones much higher at 10 to 11. And then if we look at the recrystallized rings that form together with our aquagite, when we had the partial melting and the fluid fluxing, we see that the oxygen isotope signature is lower. And this is exactly what would be expected in a rock that has been flushed by fluids that derive from former serpentinites. So that would be an additional evidence that we have this system of dehydrating ultramafic rocks, fluids release, interaction with mafic rocks or sediments, partial melting, and that is then the removal of the melts. That's that was a good sign. So now the question is, let's have a look at another scenario, and that is so far we kind of looked at these normal steady state subductions. We have oceanic crust, always about the same amount of hydration. What happens if in a subduction zone an area arrives into the subduction zone that has highly more water? It is much more enriched in water. And a typical area where this can happen are continent-ocean transitions. My colleague, Janet Manajal, he studied these continent-ocean transitions for years, and there is this kind of 50 to 100 kilometer wide zone between the continent and where, before we have the true oceanic crust forming, where we have a lot of exhumed subcontinental mantle getting very close to the seafloor that can be extensively serpentinites. So this is a rock type that is has much higher capacity to store water. So Carlos schematically showed that is a typical normal oceanic lithosphere here with a water content. And then as we come into this hydrated mantle, going over into the continental crust, more than 5 times more water. Now, the question is, do we have any, has that any impact on the arc system above? And Carlos studied rocks from Togo, West Gondwana origin, so gabbros that formed at about 670 million years, and then by 30 million years, they were pushed down to the base of this very thick arc. And so what he tried to reconstruct is how this arc crust was growing as this subduction zone came to an end. So we have this transition where we had first the normal oceanic crust subducting, and then towards the end of the subduction cycle comes this serpentinized mantle. And what we have seen is that when at the time when the serpentinized mantle arrived is that the magma production rate dramatically increased, and we have the formation of this arc thickening, so really growing from below. And then he compared that also with what happened on top. So he looked at the frequency of igneous granitic zircons in the same arc section. And then even better, he looked at detrital zircons in the adjacent basin. And what we see is that we have this dramatic increase of arc inflation, and that this is called the flare-ups, where crustal production dramatically increased from the more or less steady state before. And the interpretation of that was, our interpretation is that this was due to this increase of flux when rocks arrived that are much, much more hydrated than the rocks that entered the subduction zone before. So this shows this important link that we don't need to know only the systematics where the dehydration reactions are and then how they interact with the rocks, but we need to see also how the water is distributed, because that will impact on the amount of crust that we form. And that brings me to the last part of the talk. So out of the case studies, what we see is that it is actually quite important to see there and how much hydration there is in this incoming oceanic lithosphere. And this is actually quite a tricky problem. So let's have a look at these different places where we can have hydration. So we have discussed the mantle wedge, and we have seen that the kind of the hydrosphases are terminated at about 80 kilometer steps. So while we can hydrate here, this is a kind of limited for the serpentinites to about 80 kilometer steps. What we have seen is if we have chloride-rich melanges, then the dehydration can go deeper down up to 100, 120 kilometers. So that is one way of bringing water here to the locus of partial melting. Then we have two other areas where we can where we can hydrate the oceanic lithospheric mantle. The first one is, of course, at the spreading ridges. And here is very important that we distinguish between fast spreading and slow spreading. When we have a fast spreading, we form these 7-8 kilometers of basaltic crust, which kind of shields the underlying mantle from being hydrated. So it's much more difficult to incorporate a lot of water in a fast spreading oceanic lithospheric mantle. On the other hand, when we have the slow spreading ridges like in the Atlantic today, we have the spreading is more significant than the formation of new crust. And so we have sometimes these oceanic core complexes where oceanic lithospheric mantle is brought close to the surface. In these regions, we have a huge amount or huge potential for serpentinization and water uptake. And then there is another very tricky region that we have very little constraints on, and that is the bending of the plates. So César Raneo and co-workers, they have convincingly showed that during this bending, cracks can form that penetrate into the mantle, in the oceanic mantle, and that along these cracks, there is partial serpentinization of the rocks. So that has been done by comparing seismic wave speeds from this kink region to the flat-lying part of the oceanic crust. But how deep that serpentinization goes and the extent of serpentinization is still is not clear. And so this one would probably represent then the deepest part of hydration. And as this is the deepest part, it will be then also the coldest as this water goes into subduction. And so this brings me to the last bit of the talk. We want to have a look now if this water is really released when we have the hydration in such deep levels of the oceanic lithospheric mantle. And so I quickly introduce as a last bit the concept of the anhydrous nose. So we blow up, so far we have studied the kind of the region down here. This is a compilation of Ivan, and in the warm colors, these are all hydrous phases. So that's our antigorite, chloride, and the alphabet phases A, B, D, E. All phases that can host weight percent of water. And they define in the mantle hydrous part, where we are able to host weight, 5 to 10 weight percent of water. And then on the right, we have the fields of our anhydrous phases. In the blue colors, now that's the olivine, autoparaxine, garnet, where we just have traces of water in point defects. And so we have here these anhydrous nose, and we see that were the subduction geotherms that we discussed before, where we have our dehydration reactions nicely in these 100 to 120 kilometers depth, and then we go into essentially, as a result here, we are in the nominally anhydrous region. But if we have now in the interior of the slab much colder temperature, it is possible that we actually don't release the water that we are storing there, because we go here from hydrous phase to hydrous phase to hydrous phase. And this could be a way of bringing actually large amounts of water way down into the deeper mantle. And so this is a thing that is that is quite tricky. And what we see here, what is the decider in this game is the position of this cold nose. If our subduction geotherms pass through this cold nose, we lose the water. If we avoid this anhydrous nose, then the water can travel down and down and further down into the mantle. And quite interestingly, there have been very few experiments in this very critical part of the phase diagram. So Shane did quite a good series of experiments exactly in this region of this anhydrous nose, and I just picked the main features. Is here we have our chloride again, extending to higher pressures and higher temperatures than in previous studies. Previous studies would have had chloride just in the bottom corner here. Then we have two other main players that haven't been considered really in the past. So one is magnesium sursulfide, another hydrous phase containing aluminium, like chloride, about 7.2 weight percent of water. And here another one, 11.5 angstrom phase with 7.2 weight percent of water. And as we can see now, if we take the stability fields of these phases, map them on, we see the two hydrous noses, or the anhydrous noses that we have here. That would be for chloride-rich rock types, melange type rocks, and this one would be for a chloride Harzburgite here. And here we have our subduction geotherms, so the Mariana top slab geotherm, also with the revised position of the anhydrous nose, will still have the dehydration here at 100 to 130 kilometers depth. Tonga might be just scratching at the coldest subduction zone, presumably the coldest one, just scratching and opening up the possibility that some water might be transported to the deep mantle with the 11.5 angstrom phase. But then if you look for the Marianas, the temperature at the crust mantle interface of the subducting plate, then we see the temperature is much colder, and they go really, they don't pass through these anhydrous nose. So in these cases, then we have the large possibility to bring water to the deep mantle. So from this set of experiments, what we have seen that we have a significant shift of these anhydrous nose from here to up here, and that slab geotherms probably the hotter ones, they will still dehydrate, they will release the fluid, and then will lead to new crust. Whereas the geotherms that we have in the interior of the slab, there we have the potential of having much larger amounts of fluid stored, but we are not sure if and what the amount of this fluid will be released in order to form new crust. And so this is kind of the point. So it's an open question in this game of dehydration reactions, mass transfer, and deep water cycle. So that's the last slide. So I hope that I have shown you that we have the tools to locate these dehydration reactions, and that they have quite an important impact on many properties of the slab-mantle wedge system. Then we have seen that in order to have mass transport that is scaled with the amount of water that we have, if you have a lot of fluid coming through, there's periods where we can produce a lot of new crust. And in order to have actually significant recycling, I would suggest that melts are needed. And then the link to the deep water cycle is that we have these different positions of hydration in the slab that we have to consider. And this one is more difficult, how it will scale with the thermal structure of the slab. And here I open a can of worms, appropriately for a Thursday afternoon, is when we start to think now about the evolution of Earth, that these subduction geotherms might actually change over time. Problem is becoming very is tricky now. So if we assume the evidence that we have from the natural rock record is that we firmly can demonstrate that cold subduction started at 620 million years ago. So if cold subduction only started then, we might have been pumping water down into the deep mantle that hasn't kind of reached yet, hasn't come out at the mobs yet. And that would mean that our deep water cycle, as I introduced in the start, is not in a secular equilibrium. It might also indicate that the way of crust formation might have changed over the evolution of Earth. And that what we see now as the main way of producing continental crust can be tracked back to a certain time. But as we say, the position of our dehydration reactions, they will move as the temperatures change. It's all interconnected, has to be considered. And that is actually kind of the outlook of where this is going to head, is that we want to investigate more how the deep water cycle over the evolution of the Earth has impacted crust formation. And so I stop more on a question than on an answer, but I'm happy to take questions from the audience. Thanks for your attention.
Some questions from the audience? Matt?
Yeah, what's the deal with this 620? Did you pull that out of the hat?
So 620 is the oldest, coldest ultra high pressure eclogites. So these are the ones that have kind of go through lawsonite stability. So the eclogite gives you high pressure, but then you can have high temperature eclogites, 800 degrees, 1000 degrees, or you have the ones that at Subak were more in the 600 to 700 to 800. So from the geological record, this is the onset of PT in eclogites that follow a very cold geotherm.
What if the older ones were just destroyed?
Exactly. So that is the question. Is it a preservation bias or is it a switch in the system? And so that is one of the questions that we try to follow on to find out good proxies for subduction geotherm. Because as you're completely right, the further we go back in history, the less relics of actually subducted rocks we have, and we don't know.
So by this story, if it's correct, we put a whole mess of water at 620 million years ago, and we're still waiting for it to come on.
So we might have been putting more down than what comes up. Yeah, absolutely possible. Yeah.
Thanks, Jörg. Maybe this is a good time to ask if you can expand them on what does this mean for the origin of water. Is there anything in your studies indicative of the origin of water?
Yeah. So yeah, I cannot comment too much on where the water initially comes from. No, we can speculate. So the thing is, it could be just primordial water now, accretion, and then it would be in the interior, and it would outgas over time, and then would form the oceans, and then would start to be recycled again. So that would be one view. The problem here, or the problem that is a little bit unresolved, is the moon forming impact. So kind of when you have everything nicely established, you whack the whole system with this big body, and there, as far as I know, it's not so clear how much of the volatile phases were retained and how much of the volatile phases escaped. Clearly, there is later on is a late veneer, so there is not, we know that the material arrived later from comets and carbonaceous chondrites, and that will have contributed to some of the water. But the thing is that because of these uncertainties, nobody really knows the inventory of H2O in Earth. So Richard, I think that's a fair comment. It's one of the key elements, but is one of the ones that we have least constraints how much there is there. And so if you look in the literature, the kind of amount of ocean masses that are in the Earth's interior, they vary from about half an ocean mass to 10. So factor of 20 uncertainty.
Yeah, I think I have a question.
When you talk about dehydration of the hydrous minerals, why didn't you talk about amphibole?
Okay, yes, so amphibole has been for a long time the favorite, no? That if you go in many textbooks, is amphibole is still there. So the problem with amphibole is, I'll just take you back to one of them. So the problem is the amphibole, especially in the mafic rocks. So the amphibole stability field is stretching somewhere 2.5 gigapascal, and then it goes around here. So amphibole dehydration in most rock types occurs at 4 arc depths. So that's also when you look in most eclogites, is that the blue schist to eclogite transition occurs at the depths that is would be positions in the 4 arc. So they are just not stable deep enough to be an important water carrier in the subduction zone. So what is better is lawsonite in the altered oceanic crusts. That is a better candidate. And in super altered oceanic crust, magnesiochlorite might be another one.
Okay. On Zoom, we had Audrey, who asked a very long thing, but he left, so I copied that and emailed that to you. Other than
I
that,
don't see him.
and other than that, we had Andrew Berry, who asked a simple question of what percent of the slab is initially hydrated, assuming it's carbon.
So I would like to answer to this question as well. So,
Okay.
so this is a very is really as we see, because it's all linked between this dehydration, melt production, how much we transfer is related to position and amount of hydration. It's very is a very tricky problem. So
Is there a reasonable range that you can think of?
well, the thing is, so the thing is that they are the ocean drilling. So when they have when they drill the uppermost part, but the basalt is about 500 meters.
1,000.
Okay,
Complexes, but you're right, we don't know.
Yeah.
In place, we don't know what the water content is of the gabbros down to the moa.
yeah. So the gabbros are largely unconstrained, and then the lithospheric, oceanic lithospheric mantle, we don't know. So
You have to look at the camera, nothing, right? It's,
Yeah. so it is one of the main limitations when we want to start to do this more in a quantitative way, is that we don't know the amount, but also the distribution in depth, which is a very key figure.
Okay, before we move to the next.
Can I ask a question apropos of this conversation?
Yeah.
You're very well done. The example, and you mentioned the Atlantic as being a place where there is slow spreading going on, and the arc that is receiving, there are two arcs that receive Atlantic plate in a subduction zone. One is the Lesser Antilles, and the other is the South Sandwich Islands. The Lesser Antilles is a recent paper, Nature Geoscience or Nature, about the highly serpentinized nature because of the multiple transform faults that are along the Mid-Atlantic Ridge that go down below the Lesser Antilles. And that paper shows that along the strike of the Lesser Antilles, the size of the volcanoes, the mass flux of magma, is correlated with the amount of water, and it correlates with the number of transform faults, serpentinized transform faults that are going into the arc.
Super.
So it's a really good example of what you described.
Thanks a lot. Yeah, I haven't seen that, but I'll chase that up. Thanks,
George
Richard.
Cooper, I think, is the lead author, but it's the Blundy.
The Blundy crew.
Ghost,
Yeah.
group that are doing it. I've done that.
Okay, so before we move to the next question, I'd like to remind everyone that after this we have a social hour. Does that mean that there are drinks?
Yeah.
Okay, so there are drinks downstairs. Perfect. Caroline has a question. Now, would you like to unmute yourself and see if it actually works? Because it did work last time and we could hear people.
Hello, can you hear me?
I don't think we're hearing anything.
Can you hear me?
But I'll just read out the question. Caroline Deakin says, thanks for a fantastic talk. For the last part on the anhydrous nose, if some water might be transported to the deeper mantle for cold slabs, does this mean we might expect less dehydration in those reduced arc flux above cold slabs? Are any such variations observed?
Yes, that's possible. That is absolutely possible. The crux is really that the seismics, they give kind of the studies that have proposed that we have this hydration in this oceanic slab. They give a bulk property. So we don't really know if these are along cracks that go deep, if there is a more penetrative distribution. So we don't know the distribution. And at the end, the distribution will be key. Kind of if you have more, a higher degree of serpentinization very close to the oceanic crust mantle interface, there's a much higher chance that that will be liberated. If that goes deeper down in the slab, then the conditions are not favorable. So it really depends on the starting condition, on the initial way of serpentinization in this mantle part of subducted mantle part to answer this question. The thing is that for the Tonga, as it is a very cold subduction, there we have a good possibility that we can remobilize a lot from the slab through these chloride-rich rock types that are in the melanges at the slab-mantle interface. So they would be very favorable for having mass transfer there. And so the contributions are, the thing is also, we have no way at the moment of tracking to see where the water comes, because what we need to keep in mind is that the serpentinites, they impose only very few elements. The serpentinite is very depleted in trace element. So as soon as we interacted with with the basalts or the sediments, the serpentine signature is lost. And one of the only element system that might be able to check the serpentine contribution would be the boron isotopes, because that is one of the main contributors to the arc. It could be the boron from the serpentinization. So that would be a field, a target to try to distinguish the different regions of serpentinization, how the boron isotopes vary, and if you can see systematics in the arcs.
Killer answers, thanks. Now I've seen Kim, I've seen Anthony, but it's past 5, and because you are here, we can say thank you again. Let's have those questions over the links downstairs.
Another important hydrous fluid.